Hello dear students. In this lecture, we will try to understand how the energies are distributed in a plasma, considering the fact that plasma can be treated as a gas. So, in the case of a gas which is in thermal equilibrium, let us say we are going to discuss about plasma as a gas. Right. So, when you say a gas is in thermal equilibrium, that implies that the particles can have all possible or all probable velocities, right? And how these velocities are distributed can be given generally by a distribution function, and for an ideal gas we can take the Maxwell or Maxwellian distribution. Let us try to understand what is a distribution. What is a distribution? Let us say if the particles, there are 10 to the power of 20 atoms or molecules are there inside this gas chamber, the system that you have taken, then not all particles will have the same velocity, let us say the highest velocity, not all particles will have the lowest velocity. They will obey a distribution function. So, then let us say it will look something like this, which means most of the particles, if you have this velocity and if you have this function which is on the, or let us say number of particles on the y-axis, what it says is that if you, there will be a lot of particles will be there which will have an average velocity. The smallest velocities will be possessed by some molecules, some particles, and the largest velocities will also be possessed by some, right. Now, is it possible that a similar type of distribution is also expected in plasma? Because plasma is also an ionized gas, right. Now, for this, let us say we have to consider if all the particles are moving in the same direction or not. Of course, you can make all the particles to move in the same direction by applying an external magnetic field. That is not a very difficult thing, right. If you take one dimensional picture for a plasma, the Maxwellian distribution function can be written as, let us say f of u is a exponential minus half mu square by kBt. This is nothing but a e to the power of minus e by kBt that we are familiar with, right. What does it tell? It tells that how, if the, for given velocity, what is the probability? Let us say for larger velocities, the distribution function will be smaller, the number of particles which will have this velocity will be smaller, and things like that. So, where kb is the Boltzmann's constant and fu, the function, can be the number of particles per unit volume with a velocity between u and u plus du. So, what is fu? F of u is number of particles with velocity between u and u plus du, right. Where what is u? U is, by the way, velocity in one dimension. Now, if you want to find out the density of number of particles per unit volume, let us say if you are interested to find out what is n, the number of particles per unit volume, then obviously what you have to do is you take n is equals to minus infinity to infinity f u du. So, you integrate the entire function to find out the total number of particles per unit volume. Now, for a normalized one-dimensional Maxwellian distribution function, what you can write is, for a normalized one-dimensional Maxwellian distribution function, you can write it as minus infinity to infinity f u du will be equal to 1. When you say it is equal to 1, you are referring to normalization. So, in essence you are writing minus infinity to infinity a e to the power of minus m u square by 2 divided by kBt du is equals to 1. So, if you solve this integral, you will realize the value of constant is square root of m by 2 pi kt. It is in the form of e to the power of minus x square multiplied by a constant. So, you will realize that the value of a is something like this. Now, how is this distribution function important? For us, the width of this distribution function, the width of the distribution function is, what is it? Is a measure of temperature. Is a measure of temperature. What is temperature, by the way? Temperature is a measure of the molecular energy, the mean molecular energy of a sample. If you take a gas, the mean molecular energy is represented in the units or in the language of temperature, right? So, temperature is proportional to the average kinetic energy of the system, obviously, because both of them convey the same message about the gas, right? So, temperature is proportional to average kinetic energy of the system. It is proportional. We are not saying that the average kinetic energy is temperature. No. These two things are directly proportional to each other. So, the average kinetic energy is a measure of the temperature. So, how do we calculate the average kinetic energy? Let us say E average is integral minus infinity to infinity half mu square fu du divided by minus infinity to infinity fu du, right. Now, let us say the particle has some thermal velocity and because of it some kinetic energy mvt h square is equals to kBt, because by the virtue of its temperature it has this energy kBt and this energy must be equal to the kinetic energy of the particle. So, we can write the thermal velocity, that means the particle's motion because of its temperature can be represented in terms of the thermal velocity. So, thermal velocity is 2 kBt by m, right. Okay. Now, let us say for simplicity we are trying to solve this E average, right. Let us say we write y ratio as u by Vth. U is the one dimensional velocity, Vth is the thermal velocity. So, using this representation of y is equals to u by Vth, we can write the distribution function fu as a times exponential minus u square by Vth square, because you have written kBt, the thermal energy in the units of half Vth square, right. So, E average, using this we can write E average dy is equals to du by Vth, which implies du can be replaced as Vth dy. Okay. Using that, we can write the average energy of the sample as minus infinity to infinity half m y square VTH square. You see, where did we get this? Because U is equals to Y times VTH, right? From this, you see this, making an appropriate substitution, m y square VTH square A exponential of minus y square VTH dy. So, this is obviously du, and this is after substitution, and this is again substituting y is equals to u by VTH, right. The same expression that you see here, here is now written like this using the substituted variables, right. Once we know what it is, we can get rid of all these things, divided by a times integral minus infinity to infinity exponential of minus y square VTH dy, right. We try to evaluate this integral. E average is half m VTH cube. The integration is with respect to y. So, it only makes sense we have all the terms which involve y inside the integral and everything else, a constant, be outside the integral. Exponential of minus y square times y square dy divided by a VTH. If you are trying hard to follow what I am doing on the board, you can try working it out, all the steps. I have not missed any algebra steps in between. So, you can work out by just looking at what I am trying to do, right. So, this is what we have to solve now, right. Let us see this integral of minus infinity to infinity y times exponential minus y square y dy. This integral can be evaluated like this, which will be equal to minus half exponential of minus y square times y between minus infinity to infinity minus integral u dv minus half exponential minus y square dy. So, this will simplify to half minus infinity to infinity exponential minus y square dy. Using this back into the original equation, which is, let us say we call this as 1, using this is 2, using 2 in 1, we can write the E average is half integral minus infinity to infinity exponential minus y square dy multiplied by ma VTH cube times 1 by 2 divided by a VTH right. Now, we can cancel these two things. and as a result what we are left with is half ma VTH cube divided by a VTH. Writing the remaining terms, E average is equals to half ma VTH cube into half divided by a VTH, or 1 by 4 m VTH square. What is this? Is E average. The average kinetic energy is 1 by 4th m VTH square. Is there any relation between the kinetic energy and the thermal energy earlier that we have seen? Yeah, half mVTH square is kBT. Using, let's say we name this expression as A. Using A, we can write 1 by 4 m VTH square is equal to half kBT, right? Because half mVTH square was kBT, half of that is half kBT, right? So thus we can say that the average kinetic energy along one dimension is half kBT, right? Now we can extend this into three-dimensional picture, or we take the distribution function. It used to be f of u. Now we have f of u v w is equals to a times exponential minus half m times u square plus v square plus w square divided by kBT, and you evaluate the value of constant as n times m by 2 pi kBT, raise it to the power of 3/2. If you follow the same process as we have followed, the average energy E average is triple integral minus infinity to infinity, this one f times the exponential part times the energy, all that, divided by integral over minus infinity to infinity a the exponential part and du dv dw, same du dv dw. If you do all that, then the average kinetic energy along three dimensions would be 3 by 2 kBT. So E average is 3 by 2 kBT, average energy along three dimensions. As we can interpret that, average energy is half kBT along one degree of freedom, or when velocity is in one direction. When the velocity is in all the directions, we can say that it is 3 by 2 kBT, right? So this is just to know that how the energy is distributed in plasma or in a gas. Now plasma is considered as a gas, right? So in plasma physics, we have a practice of writing temperature not in the unit of Kelvin, but rather in the units of temperature in the units of electron volt, right? So E average is 3 by 2 kBT. A gas at 1 Kelvin, let's say, a gas at 1 Kelvin will have an energy of kBT, right? So this is the energy, you see, this is the energy. How much energy is it? So energy has to be, let's say, if energy is 1 eV, if it is 1 eV, what it means is 1.6 10 to the power of minus 19 joules, right? kBT is this. Now the kBT, the thermal energy, if it is equal to 1 electron volt, which means 1.6 10 to the power of minus 19 joules. Now, the temperature that is responsible for this energy can be calculated by dividing 1.6 into 10 to the power of minus 19 divided by 1.38 into 10 to the power of minus 23. I have substituted the value of the Boltzmann's constant, right? Now, if you do this, you will realize that 1 electron volt is equal to this much. How much? 11,600 Kelvin. So, this is the conversion factor. So, both of these two things are same. 11,600 Kelvin, how much is it equivalent in the units of energy? It is equal to 1 eV, right? Or you can use the conversion factor wherever it is possible. So, because the scale of temperatures in plasma physics is very, very high, so you often encounter very large temperatures. So, it is convenient to express them in the units of electron volts rather than in the units of Kelvin. So, we can keep something in mind like this. 1 electron volt plasma is equal, or 1 electron volt plasma is something that is existing at a temperature of 11,600 Kelvin. So, temperature that is required to produce plasma is very high. We already know how to produce plasma: solid to liquid to gas to plasma, right? So, that means that the amount of energy that you have to spend to create plasma is very, very high, and this very high values of temperature are often represented in the units of electron volt, but not in the units of Kelvin, right? So, for example, many plasmas can have temperatures of, let us say, 10, 100, 1000 Kelvin. So, rather than writing this like this, we write its equivalent, which is nothing but 100 electron volt plasma. So, the notation that we use in plasma physics is that it is a plasma at 100 electron volt. What it means is that 1 electron volt is equal to 11,600 Kelvin. You can make the conversion and say that the plasma's temperature is so much. So, in all the problems when we discuss in plasma physics, we always mention the condition of plasma in the units of electron volts and number densities per unit volume, right? So, this is some information about plasma as a gas and how energies are distributed in plasma. What we have learnt is average kinetic energy along 1 degree of freedom is half kBT, and the second most important fact that we have learned is in plasma physics the temperatures are represented in the units of electron volts, but not in the units of Kelvin.